In this tutorial, we will interface switches to our microcontroller. A switch is an input device where the microcontroller can accept input and make decisions. It may be a push button, toggle, slide, or dip switch. It gives a logic high or logic low to the microcontroller, which can be used in decision making. Like the LED, switches can be connected in two ways to the microcontroller. It can be connected in active high or active low configuration. With active high configuration, the switch is connected to the microcontroller with a pull-down resistor, a resistor from the MCU pin, to ground. The other end of the switch to the supply, when pressed, will send a high logic to the microcontroller. With active low configuration, the switch is connected to the MCU with a pull-up resistor, a resistor from the MCU pin to VCC, while the other end of the switch is connected to ground. It will give a low logic to the microcontroller when asserted. The pull-up resistor ensures a high logic when the button is not pressed, and a pull-down resistor ensures a low logic when the switch is not pressed. Because of the structure of the ports of the 8051, especially with port 0, which requires external pull-up resistors, we choose the active low configuration. As a rule of thumb, we choose a resistor in order of magnitude of 1/10, less than the input impedance of an input pin, usually 100k to 1 mega ohms. Thus we choose a 10 kilo ohm resistor. We also don't want large current flowing through our MCU when the switch is pressed, but we don't want it so large that the pull-up is so weak that it may not do its job. In addition, because of the mechanical nature of the switch, bouncing occurs that leads to false triggering. It can be solved by hardware or software debouncing. In our case, we will be adding a software debouncer to address this problem. Let us code to demonstrate the use of the switch. We use the S-bit directive in order to manipulate only a bit in a port. For example, since only one switch is connected, we only like to manipulate P20 where the switch is connected. So that the microcontroller knows that it is an input, we write 1 to the port or bit where the switch is connected. In this case, we write 1 to P20. Since we are to make decisions, we make use of if-else statements to check for the value of the switch. We know that if a switch is pressed, it gives logic 0 to the MCU, thus if we get this value we turn on the LED, else we turn it off. Let's see how it works. As you can see, the LED glows as I press the switch. To demonstrate the effect of bouncing, we modify our previous code to a 4-bit counter. Each time the switch is pressed, the variable count should increase a value of 1, and we see the results on the LEDs connected at port 2. You can see that we inverted the value of count in order to compensate for the active low LEDs. As you can see on this demo, as I press the switch, a random value is seen. In order to solve this problem, we add a small delay and check again if the switch is still pressed, then increment the value of the variable. It can now be seen that we have a more predictable output. The value increments as I press the button. Thank you. I hope you enjoy this tutorial. See you again on the next. Please don't forget to like and subscribe.